Hello everybody, welcome back to Human Resource Machine. We are at the last section of the game. As you can see, there is not far to go until the end of the game. So previously we have done the first two sections of the game, where the first section was basically a tutorial of all the operations that we can use. We had some simple arithmetic to do. The next section consisted of some more advanced comparison operations, as well as more advanced arithmetic, some additional looping, and conditional logic. So let's see what the next section has in store for us. Number 29 is storage floor. Big changes are coming, but I see you already know that. Yes, you can now access slots on the floor indirectly. What does that mean? You will see. It's going to change everything. Imagine each thing in the inbox is an address, and each address refers to a tile 0 to 9 on the floor. Your task is, for each address in the inbox, pick up the letter at that address and outbox it. Congratulations, you can now access tiles on the floor indirectly. Observe this example to see how it works compared to what you've been doing so far. Okay, yeah. So you have two instructions. They look really similar, but the first instruction, copy from 12, is just going to copy the value from slot 12 directly. So it's going to copy the number 8. I guess I can run through it and see. This is what we've been doing before. But now this one, copy from address 12, or copy from 12 indirectly, is going to look at the number in slot 12, and that number is 8, and it's going to copy from slot 8. So it's actually going to pick up the letter Y. Yeah, this concept took me the longest to understand. I must have been stuck on this for years when I started learning programming. I just could not understand the difference between a value and a value at an address. And this gets really meta because it's like everything inside a computer is a number, right? Even letters are represented by numbers. And so you have the number that's stored in memory, but then the number has an address, which is itself a number, and then you can refer to the number by its number in memory. That took me a really long time to understand. Okay, we don't need these. We know what we're doing. I'm looking at the number and I can't help thinking you can spell the word naked. Anyway, so we need refer tile 0 to 9 on the floor for each address. Okay, so we need to start from 0 and then we just indirectly access all of them until we get to well, it says refers to a tile 0 to 9 on the floor, but it has more addresses. Maybe we need to stop at 9. Oh, wait. For each address in the inbox. Okay, no. Okay, it needs me to get the letter at address 8, then letter at address 5, and so on. Okay, so inbox, we get our number, and then can we just do this directly? Copy from... Okay. What? But it's not addressed 0, it's... Oh, okay. So we have to store the value to a place on the floor, and then we can get that value indirectly. So let's copy that to here, and then copy from that number indirectly, and we can send it to the outbox. Okay, so that's just a tutorial on how to use addresses. Yep, I didn't expect any trouble with that. Next one, number 30, is string storage floor. Whoa, that's a lot of addresses. Special covert assignment. Management is requesting strings from the floor. Let's just process the strings and not read or discuss what they say. It would be impolite to read messages intended for someone else, and forbidden. Each thing in the inbox is an address of a tile on the floor. For each address provided in the inbox, outbox the requested item from the floor and all following items on the floor until you reach a 0 repeat. Okay, so I'm thinking if you get a 4, for example, then you need to get 4, 5, 6, but then 6 is a 0, so you stop here, go to the next number, 15. 15 is in E, then you get a 0, so you stop there. 7, you get 7, 8, 9, 0, and so on. So, inbox, we need the number, and then we need to be able to bump this up. We need to keep track of where we are. So let's store that in a slot. And then we need to start copying indirectly. So we get the letter in that slot. Once we get it, we can outbox it. We can bump this slot up and go back to getting the next letter, except each time we need to test if it's 0, and if it is 0, then we don't need to do that anymore. We go to the next. If it's 0, we get the next inbox thing. Jump. If 0, get the next. Okay, I think that's fine. And the message is the target XIS is awake, something XXX. Take this. Okay, we did it. The target is awake, take this. I actually want to talk about this level a bit more because it might be not very obvious at first glance. It might look like this is a really contrived exercise where you're just shuffling letters and copying them to the output, but at its core, this is actually an example of data compression. And what I mean is, if you look at the message, we know the message is, the target is awake, and we have most of these letters, the TH is missing an E, but then after that it says take this, and we don't have those words here at all. So what happened to it? Well, let's look at the input. So when we get the word the, we take T and H from here, but then the E comes from slot 15, which is the end of the word awake. And because the letter E gets duplicated in both of these words, we can actually store it only once and just have a reference to the place where we store it. Same thing with the word take. I believe what it did is took the T from number 2 and then ake, A-K-E, from the middle of the word awake. Similarly with this has TH from slot 4 and 5 sharing with the word the, and then IS from slots 17 and 18 sharing with the word is. This way, it actually avoids storing a lot of duplicate data, and by doing this, it's able to compress the message into a smaller size. This is basically what happens when you take a text file, for example, and you put it inside a zip file. The text file becomes much smaller, and that is done in a technique that's very similar to this. The compression algorithm finds duplicate strings of letters and stores those sequences in an efficient way so that it can reconstruct the original message. And the little program that we wrote, according to the directions here, this is actually a little decompression routine. This is the kind of program that executes when you decompress, when you extract a file out of the zip file. Next one, number 31, is string reverse, where we need to reverse a string. Hello. How are you today? Okay, now seriously. For each 0 terminated string in the inbox, reverse it and put the result in the outbox. Repeat. Reverse it. Okay, so what we need to do is we need to get all the letters until we hit a 0 and then lay them on the floor. We need to keep track of how many letters we have, and then once we hit a 0, we start at the back and read everything back into the outbox. So inbox, we get our letter, we copy it to, and we have a counter over here. So I'm going to use this value as a counter, copy it to here. We'll bump this up and repeat. Now our terminating condition is if our inbox is at 0. So jump if 0 in the inbox. So this loop will let us get all the letters and lay them out on the floor in sequence. Now once we're done with that, let's see. So let's say the first one is okay, we copy it. The bump is going to bring the number to a 1. The next one, if the string is only 1 letter long, is going to jump to 0, but this is going to contain a 1. So I want to bump this down first so that we get back to the position of the last letter that we wrote. And read the value at this address, send that to the outbox, and jump back to here so that we can read the next letter, except if it's 0, in which case we go back to the beginning. I think that would work. Okay, you can't bump with a letter. What would that even mean? Okay, what happened here? Jump. Oh, I got the next inbox, didn't I? Wait, let me go back and debug that, because something went wrong. I'm not sure what. Okay. What was the last instruction that I executed before this? I got something from the inbox. Wait a minute. Okay, this is where we got the last letter in our string. Bump number 14, that's correct. Jump, get the next one in the inbox, which is going to be a 0. Jump if 0, we get here, that's correct. We get down here. Oh, I just got the address wrong. We need to bump this one. That tile address, you can't indirect a tile with a letter like G. Okay, where is this? Copy. Oh, okay. There you go. We got the number wrong again. Empty value. You can't jump if 0 with empty hands. Oh. Okay. Yeah, once we outbox the thing, copy the value from here again. That way we can jump if 0. Alright, we got everything. Yeah, so as you can see, once you start getting things with addresses, it gets really hard to keep track of everything in my head, and so this is why I'm forgetting about all the basic stuff. Because I have to think about, well, you have a number that refers to a number, and that number refers to another address on the slot. So that gets a little bit tricky. Number 32 is inventory report. Inventory check, accounting verification, surprise audit. These are a few of my favorite things, so let's get started. For each thing in the inbox sent to the outbox, the total number of matching items on the floor. Okay. So if I have a C, I guess I would have to count how many C's there are on the floor. They give you a 0, which is nice. Okay, I think I got it. Get the inbox. Okay, but I have to compare. Can I subtract letters then? I have to be able to subtract letters if I want to compare them. Let's copy that to a slot so that we can store it, and maybe we don't. Okay, premature optimization, but let's skip that for now because we know we can subtract something and then add it back to restore the original value, so there's no point copying it to memory and then getting it back later. Okay, get the inbox. So again, we need to start at 0 and keep going until we hit this 0. So I don't want to use this as a counter because once we increment this, it's hard to tell when we need to stop. So maybe I'll copy from here first, make a copy of this. So this is actually our end marker, and this one is going to be our counter. So we're not going to touch the end marker because when we hit a 0, we're just going to stop. So we got our counter, we got our stuff from the inbox, our counter is initially 0. Let us subtract. Nice, we can do this indirectly too. Because I was thinking, do I need to store the count indirectly and read this value out of memory and then somehow subtract, but no, we don't need to do that. Okay, we'll want to subtract the value at the address of count. That will compare the letter in our hands against the first slot. If it is 0, okay, this is a number of matches. If it is 0, we know that it is a match, so you want to bump up the number of matches. Go back to this place, except we also need to bump up the count. Bump up our count. That is if it is 0. If it is not 0, if it is not 0, then we don't do anything. We don't bump up the total. Here, another problem is we need to restore our original value. But if we're gonna bump up the count and mess up the value in our hands anyway, then this does nothing because we need to store it on the floor anyway. Yeah, okay, that's why I said premature optimization, because that turned out to be a bad idea. Okay, let's do it the proper way. Get our inbox, copy it to a slot. Now we have that in our slot. We can just subtract the value, do our jumping, bump up the number of matches if necessary, bump up the count, and copy from 17. Get our original letter back, jump, we subtract the next letter, jump if it's 0, etc. Okay, let's see if we are handling everything correctly. We are forgetting about the end. So copy from 17, that's our original thing. Count. No, we need to check if the number at the address of count is 0. We need to see if we got to the end. So jump if 0. Can I do this indirectly? No, I can't. So I'd have to copy from bump up the count. Let's do the jump here. Copy from address count, and if that is 0, then we are done. We're done comparing with everything. This is when we output something. What do we need to output? We need to get the number of matches that we've done, output that, then jump from this because we need to reset the count, and we also need to reset the number of matches. Probably forgetting something, but let's try it. So it is going through the loop correctly and is counting correctly. I got the first one correct, so that gives me confidence that the rest is going to be correct as well. Okay, we just need one fewer instruction and make this pretty darn more efficient. Okay, I don't know about the number of instructions, but I did see a way to increase our speed. So the key here is, over here you have 2 jump instructions. So this is where we do the comparison, and if it is 0, if they are equal, you go here. If they're not equal, you go here, right? But this is 2 instructions, and the vast majority of cases the comparison is not going to match. So it's not going to jump here. It is going to take the second jump. So what if we reduce that to just 1 jump? This way we jump if 0 across this bump instruction, but in that case it would mean it's not the number of matches anymore. This is number of not match, number of items that do not match. And by the way, I want to change this to say index. That's the proper naming for this, because this one doesn't really count. I mean, yeah, it does count how many comparisons we've done, but it's also an index into the address where we're doing the comparison. So calling it index is better. But anyway, if we do it this way, then we are counting the number of things that did not match, because if it does match, it's just going to skip over this one. That's going to save us a bunch of jump instructions while we're inside this loop, and we know this loop executes many, many times. So at the end, we can't just copy from number of not matches. We need to copy from, actually let's change this, copy from our index. This is the total number of items that we've compared so far, and we want to subtract the number of not matches, which will give us the number of matches, and we send that to the out box. Let's see if that gets us the speed that we want. Nope, it's not quite there. Oh, I just had a stupid idea. Let's start version of the program. So something you might think of is you can see all the inputs here. You can see all the letters. So why not just count it yourself? Let's say C. C has 2 copies. So let's just bump this up by a couple of things. And then you can outbox this, right? That gives you the right answer for the first one. X, you have 3 copies. So let's bump this up again and send this to the outbox. A has 1, 2, 3, 4 copies. So let's bump this, send it to the outbox. You're basically cheating because you can see all the inputs. So you can just calculate everything in your head and send it to the outbox. Now this is not going to work because it says your solution works with these specific inputs, but it fails on other possible inputs, and it gives you a different set of inputs to work with. So the game does protect against you doing this. But the letters on the floors don't change. It's only the inputs that change. So we can count the stuff on the floor first to make things more efficient. So again, we know there are, let's see, we know there are 2 C's, so we can't just put this in the outbox, but what if we copy this count to here? This is the number of C's. Bump this again. The next one is going to be, which one has 3? This is the X's. So we're going to copy this to here. This is the number of X's. 1, 2, 3, 4. Which one has 4? That's A. So copy to A. And then the last one is going to be B. So now we have a count of all the letters we have on the board, and so when we see an input, there's no reason to go through everything again one by one because we've already done a total tally of all the letters. So once we get our input, all we need to do is compare that against, let's say, A. And then if it is, I want to see how it compares the letters, because theoretically if you take a letter B, for example, in the computer, I mean in a real computers, this would be like number 66, and A would be number 65. And so if you take B minus A, you'd get 1. I want to see if it's the same thing here. So let's actually do it the other way around. Let's subtract X. So if you have something like A minus X, because X comes later in the alphabet, the result is going to be negative. Whereas if you take X, subtract X, then the result is going to be 0. So I want to see if it does comparison in the way I think it would. Okay, so right now it has the letter C. It's going to subtract X, and I want to see what the result is. Minus 21. Okay, yeah. This is how I think it should work. So if the result is negative, then that means it's not X, and we'll do something else. But if it is X, we are just going to get our count of X, send that to the outbox, and go back to, no, we don't even go back to the beginning because this is where we set up the count. We only need to do this once. We go back to getting our next number from the inbox. And similarly, now I am going to, okay, let's add back our X because we're done with that. Let's subtract. The next biggest letter in the alphabet is C. Again, jump if negative. If it is not negative, then we get our count of C's, send that to the outbox, go back to our input. Now we add back our C. Next letter to test is B. Jump if negative, copy from B, send to outbox, jump to the beginning, and finally add our B back, subtract A. This is our last letter to check. If it is, that would be really weird. It should not be negative. So we don't even need to jump because we know we don't even need to add and subtract because we know once we have tested all of these, it has to be A. It can't be anything else. Or maybe it can be something else, but I'm going to assume it's only going to give us these letters and not any other letters that are not present here at all. And if it tells me otherwise, then I'll do otherwise, but right now I'm just going to assume it is A, so let's copy from number of A's, send it to the outbox, and jump back to the beginning. Let's try that. You can't add with a letter. What would that even mean? Oh, that's annoying. It lets you subtract letters, but you can't add letters back. Okay, well, let us copy that to our slot. This is our letter. Okay, subtract 2. We can't add stuff back, so let's copy from our letter again. Can't add stuff back. Yeah, I guess we only need to do that. And it is accepting our solution. 52. Look at the speed. Yeah, this is the power of pre-computing everything. As you can see, partially pre-calculating the results beforehand can save us a lot of time. But this comes at the cost of using up additional memory slots because we need a place to store those partially computed results. And this is another one of the common trade-offs in computer programming. Do you want to use more time to reprocess all the data, or do you want to use more memory to store partially calculated results? And it's often not possible to optimize both. Alright, let's get back to reducing the number of instructions now. So I'm seeing jump if 0 and another jump here, so I'm wondering if it's possible to reduce that. So let's move this up here. We just copied 217, so we will have this. We have the original letter in our hands, so copy from 17 is kind of redundant, but we're looking at this. We're looking at these jump instructions, and so moving this instruction up here makes this part clearer. Well, I couldn't find a way to reduce these jumps. I was thinking, what if I can use something like jump if negative to replace these two jumps? But that doesn't work because it needs to work with all these letters too, and the letters are not going to be 0 and they're not negative either. So that idea didn't pan out, but I did notice we're using the value at address index here, and we're using the same value here. So this is something of a redundancy that we might be able to reduce. And the way we can do that is, here we're using the value at 17, subtracting the value at address index, and all we're doing is comparing if they're the same. So the order of subtraction doesn't matter. We can copy from address index and then subtract 17, and yeah. subtract 17. This way, we don't need to copy from index again down here. We only need one copy of this instruction. And by the time we come up here, we already have the right value, and so we don't need to repeat that instruction here. That should reduce the number of instructions by 1, which is exactly what we needed. Oh, I'm subtracting with mixed operands. What am I doing? Copy from value index. Oh. Right, I need to change the jump if 0. Because we're testing if we're at the end of the string, and if we are at the end of the string, we need to go down here without doing more subtraction. Perfect, we got it. Alright, let's take our coffee break. Where is Carol?
Hey, where's Carol? Oh my god. This coffee is amazing. Back to work, ladies.
Breaking. Previous reports of Machine Army evaluate to false. Everything equals 100% fine. Whether within pleasant tolerance parameters or human skin layer, you're all going to be fine.
It's funny because somehow they always miss the most important news. Alright, I think that's enough for today. Next time we'll come back with level 34 Vol Incinerator. So that's it for today. Thanks for watching. See you next time.